Hello everyone, welcome to week 12 of NPTEL Spread Spectrum Communication and Jamming Problem session. So let's get started. ZUD ITNB ना HTNB ZUD HTNB ZZZ हाँ हाँ ना तुम्हारा स्क्रीन रिकॉर्ड नहीं हो रहा है तो तुम्हारा हो रहा है ना हाँ नहीं तो मैं वो सबमिट क्या करूँ क्या हुआ मैम के लेक्चर में जाके पढ़ाते हो मैम के लेक्चर हाँ मैम को खुद दिख रहा था ना वो एनपीटीएल का कोर्स पेज है उधर से आप असाइनमेंट डाउनलोड करूंगा फिर सॉल्व करूंगा तुम आप बिंदास बंद कर दो और कोई प्रॉब्लम नहीं है टैब मिनिमाइज करके अपना काम करो Okay, so let's start week 12. So today our course is on WCDMA and UMTS. So previously we had CDMA 2000 and IS 95 standards. We studied about them. Today we will be studying about two more standards of CDMA communication, which are WCDMA and or wideband CDMA, which is known as wideband CDMA, or and the UMTS. So first we will go to wideband CDMA. So wideband CDMA was the standard that was used for 3G telephones. So this standard was designed by the third generation partnership project known as 3GPP. The success of the second generation cell phones, especially the global system for mobile communication GSM phones, motivated the development for a successor system. Then the International Telecommunication Union (ITU) of the United Nations announced goals for a standard 3G system called IMT 2000, which will give better spectral efficiency, higher peak data rate up to 2 Mbps indoor and 384 kbps outdoor, which sounds very laughable in this day and age, but when it was developed at around like 2000, so it was revolutionary. So this should and it should support multimedia application, meaning transmission of voice, arbitrary data, text, picture, audio, video, and backward. It should be backward compatible to the second generation systems, of course. So okay, based on the above list of requirement, different groups developed different proposals, which ranged from orthogonal frequency regulation, multiplexing, or FDM based simulation, or time division, multiple access, or TDMA based solution. So two drafts were selected out of those drafts, which is the broadband CDMA or the FDD mode, also known as the frequency division duplexing or FDD mode, and another is the TCDMA, which is time code division multiple access, also known as time division duplexing or TDD mode. So FDD and TDD were the two drafts for implementation of CDMA, the two ways in which it was accepted that CDMA can be implemented in the third generation of mobile communication. The FDD mode and TDD mode were then merged together to form the WCDMA. So WCDMA is the most widely used as an abbreviation for radio access technology, while the expression UMTS refers to a complete system including the core network. So WCDMA is the radio access or front haul technique, and the backhaul or core network is included in a UMTS. So UMTS is the entire thing, and the front haul part of that is WCDMA. These two systems were then included as the European proposal for IMT 2000. Besides the Japanese European proposal, the US favored CDMA 2000 proposal also had strong support. Okay, so in order to avoid the deadlock, ITU decided to declare all these protocols and then there was another protocol which is enhanced data rate for GSM evolution or EDGE. So United Nations ITU decided to declare all these proposals to be valid modes of IMT 2000. So in the end, there was WCDMA, there was CDMA 2000, which we have discussed in the previous class, and then there was EDGE and DECT and UWC, 5 modes. So 5 modes in a single standard was pretty bad, but United Nations being United Nations had to compromise between different countries and had to get a solution which is best suited for everyone on board. After 2000, the Chinese standard, which is TD-SCDMA, has also received great attention and is becoming an important part of 3G cellular development. The standard as well as WiMAX was later accepted into the IMT 2000 family. While these were advantages of having a broad base of companies contributing to the specification, 3GPP faced some serious problem that the size of specification became large and it became complicated. So Anyways, so that is the history of CDMA. Now let's go to the technicalities. So in the WCDMA or UMTS system, which we will be studying primarily here, the physical layer of WCDMA communication between mobile station and base station via air interface. The mobile station is called user equipment or UE. Similarly, the base station is called node B. The WCDMA air interface uses CDMA for distinguishing between different users and also between users and some control channels. We distinguish between spreading codes that are responsible for bandwidth expansion of the signals and scrambling codes that are mainly used for distinguishing signals from different mobile stations. Okay. So the WCDMA air interface is that it has mobile stations which are called user equipment or UA, and it has base stations which are called node Bs. In addition, WCDMA also has a time slot structure. So the time axis is divided into units of 10 millisecond, each of which is subdivided into slots of 0.67 millisecond. So it is doing joint code and time division multiplexing. So as we can see here in this thing, yeah, so this is the TCDM, time code division multiple access. This is being implemented. So of course there is time also. There is an element of time. There are time slots. Depending on the location within a time slot, a symbol may have different meanings. So like one time slot is, you can think of as one frame. So within one frame there might be multiple subslots, and the subslots at the beginning, they may be header, and the subslots at the end are tail. So the header gives the agent which is receiving these packets an idea of what is about to come, whether it is a data frame, whether it is a control frame. And then of course there is the payload or the data or control instruction or whatever that is needed to be communicated. And in the tail there is of course some redundancy check, which CRC, cyclic redundancy check, which will ensure whether the thing that you have transmitted is correct or not, whether some bits have been corrupted or not. And finally there will be a terminator which will flag the termination of that particular frame. So the same bit in different portion of the time slot will have different meanings. Okay, so WCDMA also uses a number of logical channels for data and control information. Then they are mapped to physical channels. So the data and control information are spread across logical channels, which are then mapped to physical channels. So maybe one particular physical channel is reserved for spreading control information, others are there for time information, like that. Okay, others are for data transmission and like that. To discuss how mobile network may introduce UMTS, we have to distinguish between MS and RAN and the core network. The MS and the UMTS communicate with each other via the interface. The UTRAN consists of multiple radio network subsystems, each of which contains radio network controllers. Okay, and the core network, the UTRAN. Okay, so UTRAN is the UMTS terrestrial radio access network. So the base station communicates with this entire network. So the front facing part of that network is the node B or the base station, but behind that there is a whole backhaul which is connecting it to the internet. So that is known as the UMTS terrestrial radio access network or UTRAN. Okay, so the MS and the UTRAN communicate to each other via the interface. So instead of saying the user and the base station communicate, we are saying that the user and the entire network is communicating via air interface. Now the UTRAN itself consists of radio network subsystems, okay, each of which controls. So the entire UTRAN is divided into various radio network subsystem, which is divided into various radio network controller. Now under these radio network controller there are multiple node Bs. So node Bs are like three hierarchy down from UTRAN. So from UTRAN you have multiple RNS, Now each RNS has multiple RNCs and each RNC has multiple node Bs. Okay, the core network now the core network is basically the backhaul. So it's not the wireless communication part. That part is mostly optical or wired communication happens. So that is the backhaul. So the core network connects the different RNSs with each other and the other network like ISDN and data packet networks. Okay. So another way of looking at this UMTS architecture is to organize it into two domains. One is the user equipment domain, which is concerning the user. So it will have the mobile equipment and it will have the universal user service identity module. So this user service identity module is basically the what is known as the SIM card. So this is what is meant by SIM card. And it also has the mobile equipment. Of course, the SIM card will give a specific identity to the mobile in that particular network, whereas the infrastructure domain will consist of the CN interworking unit, serving network, transit network, home network, and application network. So these are the parts of the core network and the UTRAN. So UTRAN means the base station. Base station is controlled by controller. So base station, then RNC, RNS, these are all making up the UTRAN. So UTRAN is basically the base station architecture and the backhaul, the core network. So this is the infrastructure domain. So these are like the telecommunication infrastructure. These are not dependent on user. These are pulled by multiple users for use. Whereas user equipment domain is only concerning about things that are specific for a specific user. They are not common across users like a SIM card and a mobile equipment. Okay, so the next now we come to the next part, which is the WCDMA UMTS architecture. So the UMTS has the very end of the domain is the user domain, is the USIM or the SIM card specifically. Now this SIM card is connected to a mobile network which consists of terminal equipment, terminal adapter and mobile termination. So these are basically the same parts of mobile devices, and this together consists of the user equipment. Now this user equipment is connected to base stations. These base stations are the UTRAN. Now these base stations are then connected to the core network. This core network is here. So this is basically the core network CN. So you have your mobiles which are connected to UTRAN and UTRAN is connected to CN. So UMTS is intended to connect it to core network. So UMTS is intended to achieve global availability and thereby enable roaming worldwide. Therefore, the coverage area of UMTS is divided hierarchically into layers. The higher layer covers bigger area than the lower layer. The highest layer achieves worldwide coverage by satellite. The lower layers are macro layer, micro layer, and pico layer. So that you can see that a base station will cover a small area, maybe like a few acres. Okay, a base station will cover a area of a few acres, maybe 10 acre, 50 acre, like that. Okay, whereas RNC might take one block of a city, and the RNCs and the RNS might be covering the entire, and RNS may be covering the entire city or an entire region or an entire state even. So these are hierarchically, the UMTS is hierarchically made so that the the we when we come at the highest level possible, then the entire world is covered. If the entire world is covered by one network, then that network will allow all users to seamlessly roam. So seamlessly roam from one region to another. So because all the networks are at the end of the day connected together, whereas previously the networks were different and we had to make trunk calls in the international. That's why for in the old days, for international calls we had to make trunk calls, because they were needed to be manually connected. So the two different networks needed to be manually connected, which is no longer the case. So this was at the worldwide coverage of a mobile network is a very new phenomenon. Like it was a very revolutionary phenomenon when it was launched. Now, of course, it might seem very obvious that, of course, if you have a telecommunication network, it should ultimately cover the whole world. But back then, this worldwide coverage by one big network is was something outrageous. So it was a very revolutionary concept. So each layer will consist of several cells. So basically, like the whole world is organized into continents, then continents are divided into countries are divided into states are then divided into districts then are divided into cities. So these are like 4 or 5 levels. So there are 4 or 5 levels of division to for a particular place in the entire world. Like that, there are 4 or 5 levels of UTRAN, so that the highest level is the entire world, and the smallest level is just like maybe 20 acres around you. So now what the microcells, now these base stations of course are divided into cells. We know that these base stations are divided into cells. So these base stations are divided. Now these cells, one particular cell might have a particular like a 20-acre area, let's say. But this particular 20-acre area might be enough for a rural area. But when you are in a city, suppose in a metropolitan city, then there are lots and lots of buildings and lots of traffic in a 20-acre area. So there are lots of people in a 20-acre area. So when this population density increases, then of course one base station in 20-acre area which was working for the previous configuration will not work now. For the rural configuration will not work now. So we need to come in terms with smaller cells. So the cells are then divided into microcells for urban areas. Now, even if all areas in an urban area, in a city, basically all areas in a city do not have the same density. A hospital or a train station will of course have a very high this a hospital or a train station will of course have a very high population density. So what is good coverage for a residential area will of course not be good coverage for a train station. So there is of course much more population density in a train station. Then we come to the concept of picocells. So picocells are in specific population hotspot areas. Okay, now the maximal data rate and the highest supported user velocity will be data different for each hierarchical layer. So the particular base station, like each hierarchical layer will have different, because the thing is that at the base station level, from base station to user, it is an air interface. There is lots of fading, shadowing, attenuation. So achieving a particular data rate there is tougher than achieving that in backhaul. In backhaul, you need huge data rate because you are transmitting a lot of users' data simultaneously. So the core network will have very high data rate, and this highest layer of UTran will also have high data rate. The lower levels of UTran will be having lower and lower data rates. So by the time you come to the base station, you have a very low data rate, and the entire communication network is designed with the QoS of the lowest data rate in the user end in mind. So user is getting 10 Mbps. That means the core network data rate should be 1 Gbps. Then only maybe like the by it gets reduced and reduced after each layer, it gets reduced and reduced, and it gets bottlenecked at 10 Mbps. So the main bottleneck is the air channel interface. So we have to design the entire system with the air channel interface QoS in mind. So we cannot say because we are achieving 10 Mbps in the, because we are achieving 10 Mbps in the core network, we can say that we have a 10 Mbps network. A 10 Mbps in the core network may be a few kbps at the end user. So you have to design for the end user. So here in 3GPP, now this 10 Mbps, what I am saying is of course too much for 3GPP. 3GPP was in kbs. So in 3G, the macro layer supported at least 144 kbps. The micro layer supported 384 kbps. So like that there will be. Whereas at the picocell, because picocells are deployed only at very high hotspot areas. So if there is a very high hotspot area where there is a lot of population, so if you give the normal bandwidth there, it will be used up by only a few users and others will not get anything. So you have to have very high data rates there, as high as possible to give in the user end, because that will be divided among lots of users. Okay, so that's why in picocells it had maximal data rate of 2 Mbps. But picocells are usually deployed in a specific infrastructure, like a specific station or a building. So the mobility consideration there is less because we are not deploying picocells in highways. So the mobility consideration is less. But the macro layer might be covering a huge stretch of highway and forest land. So there your data rate might be lower, but your speed consideration, like the maximum amount of Doppler you can tolerate, will be much higher as compared to a picocell deployed inside a building, because picocells are usually used in a indoor context. Okay, so maximal bit error rates or BERs and transmission delays are grouped into sets, and you have to choose the set which will be best for your environment. So you have to choose the transmission mode based on your environment, and then you can know what you can. So now there are multiple sets of BERs and transmission delays, out of which we have to choose a particular set for our requirement. Now, if the requirement is only speech, then we can have a higher BER. But if you are doing video transmission, you have to have much lower BER. So one aspect is of course user density. Another aspect of choosing the service, particular standard of service, is the mode of communication, whether it's speech communication, text communication, or image communication, or I mean video communication. So based on that, you have to design bandwidth. You have to design the BER. So for speech communication, BER of 10 to the power minus 3 might be sufficient, but for video communication, a BER of 10 to the power minus 6 is required. So BER should be on the order of, generally, BER should be on the order of 10 to the power minus 4 or less. Okay, so audio and video streaming were two applications which were added to WCDMA, but they were of course having large delays because the BER and delay are like inversely related in those sets. Like if you want a higher BER, you have to compromise on the delay. So because BER was tough to achieve, so and video transmission needed a lower BER, then because of that lower BER, we had to settle with a large transmission delay. That is why in 3G, if you remember, if you are old enough to remember, in 3G phones that we had, the video, like if you open YouTube or something, it used to buffer a lot. It used to buffer a lot for this very simple reason that achieving a particular BER with very low transmission delay was not possible. So if you want good quality video, you have to have higher transmission delay, like you have to settle for that. So that is why even at 240p there used to be buffering, which is unimaginable now. 240 YouTube video buffering at 240p is unimaginable now, but back then even that was normal because we could not achieve that transmission delay with that BER that is needed for unbuffered transmission of video. Okay. So BERs were much less tolerated. Now, the air interface UMTS utilized frequencies from 1.9 to 2.025 gigahertz. So it was sub 6 gigahertz, of course. 1.9 to 2.025, that is 2 gigahertz. So 1.9 to 2 gigahertz. It used something just more than 100 megahertz, 125 megahertz total channel. And there was another band which existed from 2.11 to 2.2 gigahertz, which is some 90 megahertz. Now, while within these bands there was a dedicated subband for mobile satellite service, and the mobile satellite service uplink used bandwidth from 1980 to 2010. So within this 1900 to 2025 also, 1980 to 2010 was not usable for commercial mobile telephony. And similarly, the 2110 to 2200, they are also 2170 to 2200 was not usable. That is, out of the 90 megahertz, 30 megahertz were not usable, only 60 were remaining. So now these 60 megahertz in the second band, and what 15, and here 80, 95 megahertz, 60 megahertz in the second band and 95 megahertz in the first one were used for terrestrial operation, and then they were equally divided for half for TDD operation and half for FDD operation. So this is what is depicted in this table. So UMTS, you can see, starts at 1900 and within that there is a block for satellite communication, which is reserved and cannot be used by commercial applications. This is usually reserved for defense and other communication requirements, which needs to be more clandestine than common communications. Similarly, there was another from 2100 to 2220, which was again partially occupied by mobile satellite communications. Now, UMTS FDD uses the bandwidth from 1920 to 1980 for uplink and 2110 to 2100 for downlink. TDD mode does not distinguish between uplink and downlink by using different carrier frequencies, but rather by TDD can make do with the same frequency, but it will access different time slots. So whatever is remaining after FDD and mobile satellite communication, that part is used by TDD. So TDD uses the least amount of bandwidth, but why do we still not prefer TDD much? Because TDD takes a lot of time, because you cannot simultaneously transmit multiple signals. Okay, so FDD operating mode. Now, why do we need two modes? The FDD operating mode is intended to using macrocell and microcell, and TDD operating mode is intended to using picocell. Because because picocells use a lot of bandwidth, because you have to give the very high data rate, so it uses a lot of bandwidth. So the advantage of time domain division is that you can allow a signal to access the entire bandwidth at a time. So like if the signal has reached its time slot, then it can take advantage of the entire bandwidth. Whereas in FDD, it has to satisfy itself with a fraction of the bandwidth. That's why TDD is preferred for higher bandwidth operation, with the trade-off that you will have a higher latency. Whereas FDD will have lower latency, but FDD cannot give that peak data rate. That's why it is used for macro and microcell, because the data rate is relatively lower. In TDD mode, it is more difficult to handle large propagation delays between mobile station and base station, as receiving and transmitting time slots might overlap. Because TDD mode, one thing is that in TDD mode, the in TDD mode you get high bandwidth. That's why data rate is very fast. Data is propagated very fast. So a large propagation delays between mobile station and base station cannot be tolerated, because the data might be, the receiving and transmitting might get overlapped, because it is happening, all is happening very fast. So Okay, so TDD is more difficult to handle large propagation delay. That's why TDD is used in picocell. One, because it needs higher bandwidth, and second, because it cannot support high latency. So low latency, high data rate, if you want, you have to go for TDD. But it so TDD supports big asymmetries in throughput on downlink and uplink, important for application like web browsing. Now, for voice communication, uplink and downlink is mostly symmetric, whereas in TDD, uplink and downlink are very asymmetric because you rarely upload as much as you download. So the big asymmetry is supported better in TDD than in FDD, because in FDD uplink and downlink both are given a lot of bandwidth, and if that is used, then you might be wasting the uplink bandwidth, because in web browsing application, if you use FDD, because you will have a lot of reserved uplink data bandwidth which you will never be using because you rarely upload as much as you download. And for medium access, TDD employs the time code division multiple access, whereas FDD employs WCDMA. FDD employs, of course, the frequency and CDMA, whereas TDD employs time plus CDMA. Okay, that will finish our CDMA standard topic, and next we will be talking about a new concept in communication, which is interception. So low probability of intercept communication. This is mostly a defense communication application area, where instead of throughput or latency, your main focus is that adversaries, your enemies, cannot access your data. Your secrecy, the privacy, is more important than your data rate or latency. So in that kind of that kind of applications, communication needs to modify into this low probability of intercept or LPI communication. So the design of communication link to have LPI capability is predicated on the requirement for it to operate in a hostile environment, like an active war situation, a reconnaissance mission, a surveillance mission, like that. So wherein the enemy tries to detect the presence of the communicator's transmission. A typical scenario might consist of underwater or surface vehicle attempting to correspond to the satellite via transmission of a short message, and an enemy search aircraft, the interceptor, whose mission is to detect the presence of RF energy corresponding to this communicated energy. So your design has to be such that we can evade this interceptor and send our data freely. Since typically the interceptor's performance is judged by his ability to determine that the communicator has initiated a transmission and not by what might occur by this accomplishment. Okay, so the interceptor's performance is judged by the detecting the energy. Okay, the interceptor is ordinarily acquainted only with such communicator information as follows, like frequency band modulation format or spread spectrum modulation characteristics such as bandwidth and hop rate. Thus, in the absence of information related to time message initiation and the secure codes used to generate the SSC modulation, that is encryption keys. If you do not have the encryption keys of the communication, you cannot detect what message was transmitted. But sometimes even the fact that a communication is being established will give you away in a hostile situation. Like you are a ground military vehicle and you are trying to communicate with your base. You are in the enemy territory and you are trying to communicate with your base via satellite. The base is in your home territory. So the fact what you are trying to communicate is pretty useless for your enemy. Your enemy's goal is to destroy your forward position in their territory. So the fact that if they can triangulate your communication to a particular location, that will be good enough for them to send missiles to destroy your forward position. So here, even though we have employed the best of spread spectrum, that is unbreakable, but the enemy is not bothered with breaking your message. He is simply not bothered. He just wants your energy. If you are at a particular location and have sent an energy, RF energy, in the air, they can triangulate that RF energy into a pinpoint location and then send destroyers, missiles, drones to your location. So that is why we have to think of another paradigm of communication which is not focused on secrecy but on evasion. So your task is not only to secure the message but to avoid detection at all. Your enemy should not know that you are trying to communicate, not what you are trying to communicate. Okay, so this is the where the different topologies can be designed for this system. So they will be judged on the metric of simplicity in implementation. They should not be very complicated to implement, of course, and optimal performance capability. That is their performance measurement. How well they can evade interceptors. So these two together will make up the requirement. Okay, for a good design. Now, okay. So first and foremost, the communicator must maintain a low low a visual profile as possible, even not when communicating to the extreme of completely concealing its location. So second, when transmitting, the communicator should reduce his radio detectability by minimizing his radiated power. So the first and foremost principle in evading detection is that you have to reduce power. If you send in a lot of power, no matter what technique you use, you will be detected, of course. So the first thing is you have to do low power transmission, but also your power should be such that at least some energy should reach your base. So if you give too much, if you give too less energy, then also it won't work, because it might evade your enemy, but it will also evade your home base station. So it will evade everyone. It will evade both friends and enemies, which is useless. So that is where the optimization lies. It should be good enough power to reach the base, but not so high as to get detected. Okay, so the techniques used are specially designed low side lobe antennas. So you will only have antennas which will be sharp beamformed radiation pattern, which will only give sharp beamformed radiated pattern, and it will not scatter the energy around hither skither to get detected by the enemy. So if it of course transmits the energy here and there by side lobe, then it is the probability of it getting detected increases. Similarly, it should use channel coding to reduce redundancy. So as much as possible, redundancy should be reduced. Next, an optimum performance receiving system. Now, just like the transmitter, there should be some modification in the receiver also, so that it can detect very low powers. Its sensitivity should be very high. So an ordinary receiver might detect noise when a specially graded LPI signal is transmitted. And that is what you want. There are receivers, enemy receivers, there are civilian receivers, and your specific military communication should ideally register as noise to all the receivers except for those specially designed receivers in your home base. So that is what you want. You don't want civilians to know your advanced position, not enemy army, not civilians also. So the receiver should be such, with the such sensitivity, it should have a lower sensitivity, a lower noise floor than all commercially available receivers. So this is the kind of objective functions that a military communication system uses. So the civilian communication systems have very different objective parameters. Their task is to give you the maximum data rate. Your hotstar shouldn't buffer. Your IPL match shouldn't buffer. That is your first priority. But here, maybe the data may be just a short message firing at 2100 hours. Just this much might be a message. Whereas in video you have megabytes upon megabytes upon megabytes of message every second. So here the objective parameter is different. You don't need data rate. A few kbps will be very good. So even today, even to this day, when the world has moved on to 5G and is going towards 6G, military proudly uses spread spectrum, which we have stopped using in 3G only, because their objectives are different from ours. Similarly, like I said, low message bitrate and shortest possible message lengths. So you do not need an entire essay. You just need 4 or 5 words to get transmitted, and that will be good enough as your instructions from headquarters. So that's why it should have low bitrate and shortest possible message. You don't need bitrate. Bitrate is the last of your concerns, but enemy evasion is your first concern. Secrecy is your second concern. Your message should not be detected. And third is your receiver sensitivity, so that every unintended receiver will register it as noise. Each of these are attainable to various degrees and to the extent to which any of them may be employed depends upon the available implementation technologies and costs. So of course, now everything. Okay. Finally, the communicator should employ spread spectrum modulation techniques to provide anti-jam protection against the interceptor. At this, so okay. And further, apart from evading the detection, it should also use spread spectrum to, like the enemy might be employing jammer, so it should have spread spectrum detectors to avoid this jamming. Okay, at this juncture, it is also worth pointing out that a communication receiver may itself attempt to jam the interceptor's receivers, or otherwise the communicator confuse the interceptor by various decoy methods. So not only will it evade the interceptor, so here a game is going on. So here the interceptor, you have to evade the interceptor. You have to employ anti-jammer to overcome the jamming of the interceptor, and finally you also have to employ your own tactics to jam the interceptor. So multiple things are going on. It's as if there is a RF warfare going on. So here there is no straightforward line-to-line communication. There is an RF warfare. Each party is trying to block or evade other parties' RF signals. So this is, you can see, like a battlefront. So the ground user is also trying to jam the interceptor is also trying to jam the ground user. This can be modeled using a game theory, and that is a active research problem even now. Of course the techniques might have evolved, but this game is still an active research topic where the jamming and counter jamming game is simulated for defense research. Thus, the interceptor must be aware of this. At this, it is okay. So the interceptor again, the interceptor will also be intelligent. The interceptor must also be aware that the ground user is trying to jam it. So the ground user knows that the interceptor is trying to jam, and the interceptor knows the ground user is trying to jam. Both knows each other's intention, and they are playing as if they are playing a game of RF warfare. With all of these above factors individually contribute to a maximum LPI straight. So this jamming and counter jamming game, so if you can jam the interceptor very well, then even at a higher RF power, you might evade, because the interceptor is getting jammed, it cannot perform its interception. So the reason for this is that some factors are both time and spatial dependent, and the communicator may have little control over these when it is necessary to transmit. Okay. So the variables are the variables which are beyond the control of the communicator might influence its probability of interception. So these factors which influence the probability of interception are like the transmitting antenna elevation angle when pointed to the communication receiver, whether the satellite is receiving by means of a spot antenna or an earth coverage antenna. A spot antenna is for a dedicated communication link, whereas an earth coverage antenna is like a general purpose antenna. So of course the gain will be much higher, and the antenna position will also decide the gain. The weather conditions along with the weather conditions with the satellite will also depend. The also influence the probability of interception. So these are variables which are not in your control. So the satellites and this is not in your control. So a high elevation angle okay so these issues are beyond the control of the communicator. So we shall be focusing our attention on the issues that have a direct bearing on the system that we can control rather than worrying about these satellite position and other weather variables. So the intrinsic form of the LPI application is that the underlying modulation technique is MFSK, and the MFSK form is given here. So delta F is, as you know, the amplitude dependent carrier shift, and di is the value of the data symbol. So if it is like +1, +3, -3, -1, so it will be minus delta F, -3 delta F, plus delta F, +3 delta F, like that. So to reduce the chance of the interceptor detecting his message and also to combat jamming, the communicator will employ a spread spectrum modulation, which typically takes the form of frequency hopping, a combination of frequency hopping with time hopping, or DSSS using PN sequence. Thus, the four basic SS modulations employed in most LPS system transmitting MFSK data are frequency hopping pseudonoise, frequency hopping time hopping, and frequency hopping pseudonoise time hopping. So the intrinsic form of the transmitting signal are for frequency hopping, of course. Now there is a hopping code which will influence the frequency. For frequency hopping P pseudo noise, then there is a PN sequence. PN sequence symbol will influence the amplitude and the hopping code will influence the frequency. So note that the hop frequency spacing is 1 by Tc, a factor of Th by Tc larger than for pure FH to accommodate the bandwidth of PN modulation. So here we are sacrificing the advantage given by frequency hopping of managing in a smaller bandwidth, because here conserving bandwidth is not our primary goal. Military usually has a reserved bandwidth which for obvious reasons only it uses. So conserving bandwidth is not a factor that is very crucial for this application. Thus, we can safely give away the advantage that frequency hopping gives and get the 1 by TC bandwidth instead of 1 by TH bandwidth, which is much lesser. Okay, although the time hopped SS modulation types are are of interest, we shall focus our attention on the two more commonly found in LPI application, which is FH and FHPI. So a great amount of effort has been expended on the subject of properties, configuration, performance and implementation of intercept detectors. Many reports and papers are available, but the basic structure is that S by N naught will be the detection SNR, TM will be the total message time, TH is the hop time, and WSS is the space spectrum bandwidth, or WH is the hop frequency spacing. So now we have to choose the values according to our needs. The interceptor's task is to detect the presence of communication the detector okay, so since the communicator's message is not time continuous and occupies only a brief interval, interceptor desires a high probability that such message will be detected. The detection probability should be close to unity. So, but on the other hand, the interceptor does not want his equipment to indicate a state of signal detection when no actual signal is present, which is called false alarm. So, of course, no one wants false alarm. So, such a state of false alarm is caused by system noise should have a very low probability of occurrence. So, the PD and PFA, the PD should be as close to 1 as possible and PFA should be as close to 0 as possible. So, when we will detect the signal, enemy signal, we will detect it with absolute certainty, and when there will be no signal, we will not detect any signal at all, which is pretty hard to achieve. Because if you go one way, you might be detecting signals. Always you are detecting signal, whether there is signal or not. You are always going into a mode of alarm. Enemy incoming, always. Or the second, the vice versa might happen, that your PD is low, so you are not able to detect your enemy at all. You are not getting any false alarm because you are not getting any alarm at all. So both are not desired. So this is the task of our design. So PD should be as close to 1 as possible and PFA should be as close to 0 as possible. So typical values which are used in defense systems are 90% PD and 10 to the power minus 6 of false alarm probability. So extensive literature exists on the subject of interceptor detection techniques and performance. All of the various methods for detecting hop signal fall into two basic types of approach. Okay, so detecting Hoff's spread signal has two approaches. One is employing a wideband radiometer matched in bandwidth of transmission and integrating energy over the entire transmission. So basically, that spread spectrum bandwidth is pretty large, and you are deploying a radio detector over the entire bandwidth range. So that is one way of doing that. And another is using multiple narrowband radiators and to the matching to the hop bandwidth and duration of the hop pulse. That is, you are detecting only the portions which might have the particular hops instead of the entire range. But the second one is of course more better suited, but the second one is not always easy to implement because you have to know the exact spread spectrum configuration, which is much tougher to know than the entire bandwidth, because usually the entire bandwidth reserved is pretty well known, and they have military is also bound to transmitting that bandwidth because they cannot, their devices are designed as such and they cannot suddenly switch over to civilian frequencies if they want. So one is much more easier, but one needs a wide search space, whereas two is much more specific. But two is difficult to implement without knowing the exact modalities of the spread spectrum used by your enemies, which is very hard to get. The second of these two approaches implies in its generic form a requirement for a filter at each possible half frequency. So instead of getting a correlator for the entire bandwidth, you are getting a separate filter for each hop. But structures which ease this requirement have also been considered. So now they have done some optimization so that you don't have to go and integrate all the hops all the time. But anyways, so the two detector types, the multiple detector types rather, are wideband energy detector, which is very functional and generally used, and optimum multi-channel frequency hopping pulse match detector, which is two. That is, each pulse of frequency hop you are matching to that. So you are designing a match filter to each hop, but knowing each hop is difficult, especially for an enemy who will try to change up their specifics of transmission as often as possible. So this is academic. It provides an optimum performance bound, but might not be applicable for defense scenarios. Next is maximum channel filter bank combiner, which is a suboptimal version of 2, and another is optimum partial band FH pulse match detector. So it is, instead of entire bandwidth you match all the hops, in 4 you try to match some of the hops. And another is partial band filter bank combiner, which is suboptimal and as well as sub-configuration. Sub-configuration means it only covers some of the hop frequencies, and suboptimal means it does not give as good a performance as 2. So PBFBC is both suboptimal and subset, but still it is realizable. The others are complex, or even 2 is outright academic because you don't know any specifics. So 1 and 5 are what is designed in defense applications. 2, 3 and 4 are mostly for theoretical studies. So the first of these methods, as we discussed, is the wideband energy detector or radiometer. Okay, so an idealized radiometer is treated here in figure 1. So this is an idealized radiometer. So it considers a band of the entire band of the transmission. So it uses a BPF to concentrate energy in that band of transmission. Then it does a square correlation, square law device, then correlation, and then it will have a threshold. So whatever threshold it has of like whether signal is present or not, it must have a detection threshold. It will compare to that detection threshold and then based on that declare the detection. So it is a pretty straightforward. Concentrating your energy in the band, do a correlation, compare with threshold, and declare your finding. So it is a very straightforward technique. So the signal plus noise is passed through a BPF, which is square law detected and integrated in for t seconds and compared to a threshold that is designed to operate on background noise. So basically, whether your signal is crossing the background noise threshold or not, whether it is crossing the noise floor or not. If it is crossing the noise floor, declare detection. The radiometer can be shown to be the optimal structure for detecting signal that is a Gaussian random process and is immersed in a white Gaussian noise background. So your data process and your noise process both have to be Gaussian for the radiometer to be optimum. Further, the bandpass filter should be matched to the signal bandwidth, of course, so that random energies do not interfere. The radiometer considered here does not have a match filter at the input, since it is assumed that the signal to be detected is unknown in spectral shape. So the signal you are detecting is unknown, so you cannot match a filter to it. The input filter is assumed to be an ideal bandpass filter and having a positive frequency bandwidth of W Hz, which by intent is equal to the signal bandwidth. The output of the wave filter feeds the square law detector that feeds the T-second integrator. This is the classic integrate and dump radiometer. So you are integrating and accumulating. In this analysis, it will be assumed that the signal exists for T-second and the radiometer is synchronized in time with the signal at the receiver. So, of course, for the integration to work, your receiver has to be synchronized. This assumption leads to the best possible performance one can hope for, since in reality, the timing will not be known in advance and even the bandwidth may not be known in advance. The threshold detector compares the integrator output with the threshold and makes a decision on whether the signal is present. So the received signal plus noise is this. So of course you have signal and they are divided into in phase and quadrature. Similarly, noise divided into in phase and quadrature. The false alarm and detection probabilities are given here, which are functions of WT, where WT is bandwidth and the T-second integration you are doing, and the W is the cutoff of the bandpass filter. So N is equal to WT, it is function of WT, and it is function of delta, which is the threshold. So if you know these, you can derive the PFA and PD, or realistically, if you have PFA and PD targets, you can find M and delta for that PFA and PD target. The integrand of this 1.5 is called the chi-square density function. So the false alarm probability follows the chi-square density function, and the detection probability also falls under chi-square, but it is a non-central chi-square. Okay, PD can be okay. So now they have done some small changes in the PFA and PD expressions. Okay. So only the parameters m, r, and delta need to be specified, where r is the SNR, E by N naught, and m is WT, which is the bandwidth into time, and this is the so yeah, so that will be the, where did it go, 1 minute, yeah. So this will be the expression for PFA and PD, which can again be further simplified. They have done like writing in terms of a generalized Markov Q function, which you can ignore. You can just see these expressions. This will be good enough. So the only the parameters m, r, and delta. M is W into T, R is data rate, and delta is threshold, is needs to be specified to evaluate these two probabilities. Before we discuss the limitations of these problems, let us consider a Gaussian approximation. So now they do some Gaussian approximation, and with it gets PFA as the Q function of beta is approximated as the PFA is approximated as the Q function of beta, where beta is this particular expression including bandwidth, time, hop time, noise, float, all of that combined together to form beta. The Q function of beta is PFA. And if you take WT, SNR, and beta together and combine them in this way, then the Q function of that will be the probability of detection. So this is a logical approximation, and this is what can be used to do numericals, because these are of course very difficult to evaluate. So this is what is used to evaluate the PD and PFA. So if you want beta value, what you do is, usually PFA is always specified. If you want to do this kind of a detector design, the first parameter that is specified is PFA. PFA is nearly always specified. So if you have PFA, you will have a Q table. So Q value tables are very easily available in internet. So if you have a particular PFA value, you can find the value of beta by following the Q table. And once that is done, when that is done, so the QX function, yeah, so then when that is done, you can find the value of beta. Then SNR, of course, a target SNR you have in your mind, and W and T unknown. So with that, you can find the detection probability again by using the Q table. So here there is an example. Determine the minimum integration time, that is capital T, needed to detect a signal that has power level of minus 160 dB through an omni antenna of 0 dB gain, assuming that the Gaussian approximation is adequate, that is PFA equal to Q beta is appropriate. So the noise level is minus 200 dB per hertz, and the bandwidth is 10 megahertz, and so we have to find the integration time to achieve detection probability of 95% and a false alarm probability of 10 to the power minus 2, which is pretty high. So 10 to the power minus 2, so we can just open. So let's say we open Notepad and so 10 to the power minus 2 is equal to PFA is equal to Q of beta. So beta will be Q, beta will be, so just Q inverse of 10 to the power minus 2. So you go to Q table. Let's do here. Solve Qx is equal to 0.01. Okay, so so Q function is half ERFC x root by 2. So usually ERFC is what is given. So if this is 0.01, we know this is 0.01. So what you have to do is you go to Wolfram. You can use calculator also. So half ERFC is 0.5 into, so x by root 2. So x inverse ERFC of, so half going to that side will become 2. So 2 into 0.01 ERFC inverse of 2 into 0.01. No. I'll just do the calculation. So Qx is nothing but half ERFC x by root 2. So that is given to be 0.01. So ERFC x by root 2 is 0.02. So we have to go to ERFC table and find which value gives 0.02. So let's see the ERFC table. Which value gives 0.02? ERFC as 0.02. So ERFC 0.02 is given by, the closest we can get is 1.64. So 1.64 is where you get ERFC 0.02. So x by root 2 is 1.64. So x is 1.64 into root 2, that is 1.41. So if you just do 1.64 into 1.41, you get beta is equal to 2.31. So beta value you get 2.31. Now beta is WT, where W is bandwidth of transmission and T is the integration time. So T will be beta by W, 2.31 by W. W is, the bandwidth is 10 megahertz. So 10 into 10 to the power 6. So 2.31 by 10 is 0.231 into 10 to the power minus 6. So 0.231 microseconds. Am I doing something? Okay. Sorry, the beta is not simply WT. Beta is TH minus N naught WT by N naught root WT. So here you have to put beta as 2.31, and if you put all the values, the particular time you will get as 1.575. So yeah. Now the limitations of radiometer is that, of course, if there is background temperature variation, then it will change. Also, threshold is a statistical quantity, it is not certain, so you might be choosing the wrong threshold. Then the antenna performance might vary like that. So that will be from radiometer. So that will be all from my side for today. So yeah, that will be the end of problem solving session for spread spectrum communication. There will be no further problem solving classes. So yeah, best of luck for your exams. Take care. Bye.